Yeah, hi everyone, I'm George. I'm a PhD student at the University of Sheffield, and I'm going to talk to you today about a particular application of quantum field theory in curved space-time to extremal black holes. So before I dive in, it's worth just reviewing a couple of key points about QFT and curved space-time. So we're interested in quantum matter fields and how they behave on a curved fixed background as described by general relativity. And when we move away from flat space-time, we're met with a number of complications. The first being that we no longer have a preferred time-like killing vector with which to define positive frequency. And the upshot of this is we no longer have a preferred vacuum state with which to calculate observables. And so we often have to make a choice as to which is the most appropriate vacuum state to use in a given situation. The next complication that arises is when it comes to calculating these observables. This involves dealing with quantities that are defined at two distinct or more distinct space-time points. We saw this in Siva's talk at the beginning of the day. And then we have to take coincidence limits of these space-time points, and this leads to divergences which have to be treated carefully. They have to be renormalized. And this makes the calculations of observables typically difficult. So I'm going to be talking about extremal Rising-Nordstrom, or rather the two-dimensional truncation of 4D extremal Rising-Nordstrom. So this is the mass equal charge Rising-Nordstrom solution, the limit of that solution. I'm talking about the 2D case just because calculations are easier, and some of the features of the 2D case sort of carry on to the 4D case. But it's, why look at extremal black holes at all? They're certainly not particularly physical solutions. But I think from the perspective of QFT and curved space-time, they have interesting geometries. So as I'll talk about a bit later on in the talk, their near horizon limit gives rise to patches of anti-de Sitter space-time. They also have zero temperature, so you don't get the usual sort of thermal fluxes of Hawking radiation that you do for non-extremal black holes. And here's some other reasons here. But yeah, before we move on, it's just worth reviewing. I said in the first slide that we have to make a choice of which vacuum states are most relevant for a given situation. For black hole physics, there are three usual vacuum states of interest. These are the Böhler, Unruh, and Hartle-Hawking. As you gather from the title, Hartle-Hawking is the most relevant for this talk today. And this is a state that respects the symmetries of the space-time. So for 2D RN, it's 2D extremal Rising-Nordstrom, it's static. It's also regular throughout the space-time, in particular over the event horizons. It's also worth mentioning Böhler, that will come up as well a bit. That has that is not regular over the event horizons and is empty at plus or minus infinity. So we're interested to know whether a Hartle-Hawking state can exist on this particular space-time. And one approach to investigating this is to say, well, we expect observables calculated in this state to have the same regularity and symmetry properties. So can we calculate these observables, and then do they have the properties we're looking for? But again, as I said in the first slide, calculations of these observables are typically difficult. However, we can use an alternative approach to investigate observables, which was introduced by Fulling and Christensen, where you study the conservation equations to see what you can learn about components of, for example, here, the stress energy tensor. So for 2D extremal Rising-Nordstrom for a neutral scalar, this has been done. These are the conservation equations here. And if you integrate them back, you find that you can't have a Hartle-Hawking state. For this instance, it requires that the trace anomaly vanishes over the horizons, which it doesn't. But if you include a charge, so you have a charge scalar field, the conservation equations are modified, as you can see here, by this additional term on the right-hand side. So we can ask whether that gives us any more freedom with which to define the state we're interested in, a regular state across both event horizons. So we can start this investigation by looking at what these regularity conditions mean for this term on the right-hand side here. This is the renormalized current, the charge scalar field, and that's separately conserved. And if we ask for that to be conserved and to be regular across the event horizons. That tells us that we require the R component of this to vanish and the T component to just be a regular function across the horizons. So we can plug this back into our conservation equations, tailor expand for the unknown function and integrate back. And this gives us this constraint here for a regular stress energy tensor across the event horizons. You can see that in the neutral case, we don't have this T term, and this is the trace anomaly term that I was talking about is required to vanish, which it doesn't. So we've reduced the problem to finding whether we can have this regular stress energy tensor to just finding one component of the renormalized current. So all that's left to do is try and calculate this. And this is, again, a difficult calculation, particularly on the full black hole spacetime, because the radial equation can be only solved numerically. However, we can use some of the nice features of the geometry, introduce this coordinate here, and take an R going to M limit, and then this gives us this patch of Poincare ADS here. This is sort of displayed in these Penrose diagrams here. And in the near horizon region in Poincare ADS, we can actually solve the radial equation exactly in terms of Whittaker functions. We can even go a step further and use conformal invariance of the charge scalar in 2D to consider the problem on 2D Minkowski space. This just makes finding things like renormalization terms a bit more straightforward. We don't have to worry about curvature terms. So we can go to the two-dimensional Minkowski space, work through our calculation, and we end up with this horrible looking term here. These m's are Whittaker functions. They come from the solution of the radial equation. But the only sort of important piece of information in this term is this 1 over r we have at the front, 1 over r bar, sorry. And if we relate that back to the Poincare ADS spacetime or the black hole, we have this r bar squared term at the top. So the whole thing scales like r bar, which goes to infinity as r goes to m. You can see in this simple relation here. So this certainly doesn't satisfy our constraints for the state we're interested in. It doesn't even satisfy the constraints for the current, let alone the constraint equation for the renormalized stress energy tensor. So this tells us that the state we calculated this in, which was actually the Bowler state, doesn't coincide with the Hartle-Hawking state, which we investigated from the neutral scale, which was motivated by investigations from the neutral scale in 4D, where the Hartle-Hawking state and Bowler states do coincide. So just to summarize, we've shown that the conservation equations, when you include a charge for a scalar field, actually do allow for the existence of a Hartle-Hawking state at the price of constraining the renormalized current. However, unlike how it appears for the 4D neutral scalar field, the Bowler and Hartle-Hawking states don't coincide. And yeah, following on from this work, I guess the next thing to consider is the 4D case for the charge scalar field, and then maybe look at something a bit more fundamental. So see if there's something more fundamental to be said about Hartle-Hawking states for extremal black holes or for charge scalar fields in general. And yeah, I think I'll stop there. If that's okay.
Okay, thank you very much. We're a little bit ahead of time, so we have some extra time for questions potentially. So none come through yet. Hopefully someone will type something. While we're doing that, if you can just go back, your conclusions you said about going to 4D, were there any particular complications other than the extra dimensionality that you were anticipating in going up to higher dimensions?
No, it's really just the calculations are more complicated. As I said, you've got a lot of features that carry over from the 2D case. So we have this near horizon ADS region. In the 4D case, we have a two-dimensional ADS, the product of a two-dimensional ADS region with a two-sphere. It's called the Bertotti-Robinson spacetime. And so not only does that have similar features, but that's again conformally flat. So maybe even some of the relation to Minkowski-based stuff might still hold. So yeah, it is really just down to the more difficult equations to solve.
Okay, so just going a little bit further about that, then have you, if it's not too difficult going to 4D, had you considered going to any higher dimensions?
No. As I say, this is still fairly new, so it'll be 4D next, and then we'll cross that bridge when we come to it, I guess.
Cool. Okay, I was just wondering if there was any cool ADS CFT type things you might be able to do in higher dimensions.
It's nothing we've considered so far to date.
Okay, cool.